Now we're moving on to section 14.6, buffers. Here we're going to describe the composition and function of acid-base buffers and calculate the pH of a buffer before and after the addition of added acid or base. So before we talk about the chemical definition of a buffer, I want you to think of a buffer in terms of like a person being a buffer between two people that maybe are getting into a fight. So if they're trying to throw punches and you're being a buffer trying to stop the fight, you're keeping them from hitting each other, or at least hitting each other super hard, right? You're pushing them apart. Chemical buffers, kind of the same thing. So a buffer solution has amounts of both a weak acid and its conjugate base. So it's usually a salt. So you've got a metal plus the negative anion conjugate base. And these resist changes in pH when you add a small amount of strong acid or base. So you add a small amount of strong acid to a buffered solution, and the base is going to react with it basically and keep the pH from changing drastically. So whereas if it wasn't buffered, you added some acid to it, your pH might just spike or go down to very high acidity. Whereas if you're being a buffer between two people fighting and you're trying to keep one person from throwing a punch, you get in the way, you kind of keep them back, and even if that punch connects, it's not going to connect as hard. Instead of like giving someone a black eye, maybe they just kind of gently graze their cheek and they start a new relationship from the misunderstanding. Some examples of a buffered solution is something like taking acetic acid or vinegar and adding sodium acetate, which is a salt of the conjugate base. So you put that sodium acetate in water, the sodium ion is just a spectator ion. It doesn't do anything. So then you have that acetate ion, which is the conjugate base of acetic acid. So to kind of look at an example here, in picture A, you have two solutions. One of them is an unbuffered solution, and the other one is a buffer, both of them at about a pH of 8. And then once you add 1 milliliter of 0.01 molar hydrochloric acid, you see that the unbuffered solution, that color changes. So the indicator is changing to tell us that it is no longer buffered. Now this pH is way lower. It's become acidic. Whereas the buffered solution hasn't changed. So it's resisting that change in pH. So now let's look at a generic buffer, some HA acid and its conjugate base A-. Buffers are good at getting rid of strong acids and bases. So you add some OH- or hydronium or H3O, they're going to get consumed and then not directly affect your pH. So your OH- is converted to weak base of A- because it reacts with your acid in solution. Whereas hydronium is converted to weak acid HA because it reacts with your A- base. So buffers can be used to maintain a fairly constant pH. So I do some aquarium keeping, and I have my own little pH meter to check the pH of my water. And to make sure that it's operating correctly, you can actually buy powders that you dissolve them, and it'll tell you how much water to put it in, and it buffers that solution at that pH. So then I put my pH meter in it, and I see, okay, pH meter is reading 8.01, and this is a pH 8 buffer. Cool. My pH meter is reading correct. So for instance, like I was saying, acetic acid and sodium acetate buffer, there is technically a small change in pH that happens when you add acid or base into your buffer, because you are technically changing the amounts of acetic acid and the acetate ion because they're reacting away. But it's not a large amount. So, and looking at this in terms of Le Chatelier's principle, we start in the middle with our buffer solution that has equal molar amounts of acid and base. So then if we go and we add some acid to it, okay, the acid is going to then react with the base, and now we're going to have a little bit less base and a little bit more of that weak acid. Whereas if we add a strong base, now our acid's going to react with it, and we're going to have less acid and more base. But it's not a huge increase in either one. So your pH isn't changing by a whole lot. Whereas if this was an unbuffered solution, you add a little bit of acid or base and your pH is just going to drastically change. So let's look at an example, and I'm probably going to have to go to a blank screen or something to go through all this. But we're talking about acetate buffers, and they are used in biochemical studies of enzymes and other chemical components of cells to prevent pH changes that might affect the biochemical activity of these compounds. First thing we want to do is calculate the pH of an acetate buffer, that is a mixture with 0.10 molar acetic acid and 0.10 molar sodium acetate. Then we want to calculate the pH after 1 milliliter of sodium hydroxide is added to 100 milliliters of this. And then for comparison, calculate the pH of 1 milliliter of 0.10 molar sodium hydroxide added to 100 milliliters of a solution of an unbuffered solution with a pH of 4.74. So this is a lot. We're going to break it down piece by piece. So I am going to go ahead and go to a blank slide. Where's my mouse? We're going to go ahead and say screen. Go to a white screen. And I'm going to rewrite the reaction here. We're going to start with part A. So we have CH3CO2H and water. H3O plus and CH3CO2 minus. So we're going to ice table this puppy. Ice, ice, baby. H2O goes away. And we were told that we're starting with 0.10 molar of acetic acid. We're approximating 0 hydronium and 0 acetate ion. And we're losing some X amount of acetic acid, gaining X hydronium and acetate. And at equilibrium of 0.10 minus X, X, X. And I don't have it in front of me, but we're going to go ahead and assume that our X is much, much less than 0.10. So this becomes 0. And let's go ahead and find the Ka. So we go to Appendix H in our textbook. Sometimes it's kind of a pain to find the appendices. But the nice thing is if you have this online, you just click a button. And so we are looking for acetic acid. And the nice thing with Appendix H is it has lots of Kas, and acetic acid is there. So acetic acid has a Ka of 1.8 times 10 to the negative fifth. So yeah, based off of that Ka, we can definitely do our assumption that X is much less than 0.10. So now that is equal to X times X over 0.10. And then using that, solving for X, we get so let's see, we do clear 1.8 e to the negative fifth times 0.1, take the square root. Oops, now I know why I messed up. All right, let's restart this question. So let's go ahead and look at an example, looking at pH changes in buffered and unbuffered solutions. The first part, we want to find the pH of an acetate buffer that is 0.10 molar acetic acid and 0.10 molar sodium acetate. And then the second part is calculate the pH after we add some sodium hydroxide, and then we have a comparison. So I'm going to go ahead and go on a blank screen, and we're going to go start with part A. So part A, let's look at the reaction. Let's go ahead and write it down for acetic acid. We have CH3 H3CO2H aqueous plus H2O liquid, equilibrium H3O plus aqueous plus CH3CO2 minus aqueous. So let's set up an ice table. Ice, ice, baby. H2O is 0. We know our starting hydronium is about 0. We're told 0.10 molar for acetic acid. Now acetate, for pretty much all the ice tables we've done to this point, we've assumed all of our products were 0. But here, the acetate ion, we had already added it in by doing the salt of it. So we have a starting concentration of acetate. So the acetic acid is losing X or gaining X hydronium, and the acetate ion is also gaining X. So at equilibrium, we have 0.10 minus X, X, and 0.10 plus X. Now the Ka for this reaction, we go ahead and look up appendix H. We want to find that for acetic acid. And it has a Ka of 1.8 times 10 to the negative fifth. And so using that, we can tell that X is going to be much, much less than 0.10. So these guys, both of these X's go to 0. So then the Ka is equal to products X times 0.10 divided by reactants 0.10. So those 1.10's cancel out. So our Ka is equal to our X, our concentration. So that's 1.8 times 10 to the negative fifth. And that's equal to our hydronium concentration. So then we want the pH. A asks for the pH. So that is equal to the negative log of hydronium, which is negative log of 1.8 times 10 to the negative fifth. And this gives us a pH of 4.74. So we've done part A now. And so now let's go ahead and look at what part B wanted. We wanted the pH after we add 1 milliliter of 0.10 molar NaOH. And we're adding that to 100 milliliters of this buffer. So let's first look at how many moles of sodium hydroxide that we are adding. So let's go back to a blank screen now. So we were told 1 milliliter of 0.10 molar NaOH. So 1 milliliter. And we need to go ahead and start by putting this into liters. And there's 1,000 milliliters per 1 liter. And now we can get moles of sodium hydroxide using the molarity, 0.10 moles of NaOH for every 1 liter of NaOH. So that all cancels. And this gives us 1.0 times 10 to the negative fourth moles of sodium hydroxide. So we also know the amount of acetic acid, because we were told 100 milliliters of acetic acid. So we have 100 milliliters and 1 liter per 1,000 liters. Or, I'm sorry, 1 liter per 1,000 milliliters. And we know that the molarity of the acetic acid is 0.100. So we have 0.100 moles of acetic acid for every 1 liter. Sorry, that one other wasn't 1 liter of NaOH, it's 1 liter solution. 1 liter, those cancel. And so this tells me I have 1.00 times 10 to the negative second moles of acetic acid. So then, let's go ahead and make an ice table using moles. Now, instead of molarity, we're using moles. So keep that in mind, but we can still do this. Let's see. Or, we can go ahead and just kind of write this out without using a nice table. We know that the amount of acetic acid remaining is going to be 1.0 or 1.00 whatever times 10 to the negative 2 moles, which is what we just calculated, minus 0.01 times 10 to the negative second, which is, or minus 1.0 times 10 to the negative fourth. So this is the amount of the base that it's reacting with. 1.0 times 10 to the negative fourth. That's this number. Because we're reacting all of the hydroxide away. And so this gives us 0.99 times 10 to the negative second moles that are remaining. Now the acetate, we already have some acetate present, which is the 0.100 molar, which the acetate is going to be the same thing. There's 100 milliliters, so that means we have 1.00 times 10 to the negative second moles of acetate ion. And it's going to increase in concentration because that strong base is being converted to weak base by the acetic acid. So it's going to gain that 1.0 times 10 to the negative fourth moles. Hi, Sprite. You cannot help me. Thank you. Sprite's decided she wants attention. Okay. And so now its total is going to be 1.01 times 10 to the negative second moles of acetate ion. So now to get their concentrations, our total volume is going to equal 100 milliliters plus that 1 milliliter. So we have 101 milliliters, which is 0.101 liters. So our concentration then of acetic acid, CH3CO2H, I've just been putting AA, then is equal to 9.9 times 10 to the negative third mole. So we just put that in regular scientific notation. Divided by 0.101 liters. This is 0.098 molar. And then our concentration of the acetate ion, which is sodium acetate, CH3CO2, equals 1.01 times 10 to the negative second moles divided by 0.101 liters, and that's 0.100 molar. So if you want, then you can go ahead and calculate your pH. Doing kind of similar concentrations, and you would end up getting that the pH is 4.75, which doesn't vary that much from what we started with. So we start with 4.74. So you would take these values, put them in an ICE table, so like part A, and then you would get a pH equals 4.7, what did I say, 4.74, or 4.75. So that's a really long problem. If this were like an exam, I would only give you part B. I wouldn't make you do A and B, for instance. I would only give you one of those parts. So then the last part, for comparison, calculate the pH after 1 ml of 0.10 molar sodium hydroxide is added to 1 ml of a solution of an unbuffered solution with a pH of 4.74. So because we're told we start with a pH of 4.74, then the initial hydronium concentration is equal to 10 to the negative 4.74. So that's 1.8 times 10 to the negative fifth molar. And then we added in Okay, oh, sorry, now we're going to go ahead and change this to moles. So we were told this is 0. Let me just erase this. So now we have 1.8 times 10 to the negative fifth molar, which is moles per liter. So I'm just going to rewrite this as moles per 1 liter. And we were told that we added this to 1 milliliter. So we have 1.0 milliliter, and then we have 1 liter per 1,000 milliliters. So we can see our units here canceling. So now we get moles. We added 1.8 times, or we originally had 1.8 times 10 to the negative 6 moles of hydronium. And then the hydroxide that we added, okay, we had 1 milliliter. Oops, I'm sorry, this over here wasn't 1 milliliter, this is 100 milliliters. So we had 1 milliliter of base that was added. And this base, we have 1 liter per 1,000 milliliters. And that base had a concentration of 0.10 moles per 1 liter. So we see our units cancel, and then we get the moles that we added. 1.0 times 10 to the negative fourth moles of OH minus. And the reaction that happens here is H3O plus, I didn't mean to put that in brackets, so many concentrations, plus OH minus makes 2 H2O liquid. So you can see that there's a one-to-one stoichiometry between hydronium and hydroxide. So we have excess hydroxide. So the amount of hydroxide remaining, since it's 1-to-1, is going to equal 1.0 times 10 to the negative fourth minus 1.8 times 10 to the negative 6, because we're using up all of the hydronium, and so the amount of hydronium reacted is going to equal the amount of hydroxide that we reacted. And so then that is equal to 9.8 times 10 to the negative fifth moles of OH minus. And if we divide that by our volume, which is 0.101 liters total, this gives us a molarity of 9.7 times 10 to the negative fourth molar of hydroxide. Also, I apologize for how long this problem is. You're all probably just done already. I'm right there with you. So now we know how much hydroxide. And we can go ahead and calculate the POH, since we know the hydroxide concentration, the negative log of OH, which is the negative log of 9.7 times 10 to the negative fourth. So our POH, let's go ahead and punch this into the calculator. 9.7 e to the negative fourth, and we want the log. So this is, the POH is 3.01, and pH is equal to 14 minus POH. And so then we get a pH is equal to 10.98 or 10.99 for part C. I'm sorry, that question was just awful. If I were on an exam, I would not give you all 3 parts. I would give you 1 part of that. But basically what they want you to see with part C is adding that sodium hydroxide really pulls that pH up from 4.74 to 10.99 if you put it in an unbuffered solution. So the buffer does a good job at resisting that change. Okay, so now we have another term, buffer capacity. And this is the amount of strong acid or base that can be added to a given volume of a buffer solution before the pH changes significantly. So buffers don't last forever. They have a limited capacity of how much acid or base they can soak up. Eventually, all the acid is going to react with enough OH minus, or the base is going to react with enough H3O. So it's going to depend on the number of moles of the weak acid and its conjugate base that are in the mixture. If you have more moles of the buffer components, you have a higher buffer capacity. Once, though, it nears completion, then you start seeing large changes in the pH. So for instance, here is a buffer, and it's got this indicator methyl orange. Starts off at a pH of 8. Some acid is added, and it goes down to 7.66, but it's still that orange color. Overall, not much change in pH, but once it's gone over that capacity, but look how much liquid they had to add compared to break that buffering capacity. Once it happens, though, you see that color change from the indicator, and it goes down to 1.53. So broke the buffering capacity, and then the pH just drops. Now, if we know the concentration of the weak acid and its conjugate base, we can actually calculate the pH of a buffer system. Oh, the other thing I want to point out with buffers, blood is actually a buffered solution. So carbonic acid is the principal acid and bicarbonate ion is your base. So it's very important that your blood stay at its pH, which is generally around 7.35. Your pH doesn't change much, but maybe 0.1 in value. But if it changes by 0.4 or greater, either direction in pH, it can be fatal. So this is why things like alkaline water is complete and utter bullshit. You don't want to change. I mean, it might taste good and it's fine, but for one, it's not going to change the pH of your body, of your stomach or your blood or anything or whatever they're trying to tell you that you need to have an alkaline body. Because if you change the pH of your body, you will die. But yeah, there's not enough of anything in that, any alkaline or whatever they're trying to sell to do anything to help or hinder. I don't know how everyone to say that. It's BS. Okay. Anyway, like I said, we can calculate the pH of a buffer system if we know the concentration of the weak acid and its conjugate base. So let's look at Ka for this reaction. Okay, that would be H3O times the acid over HA. And if we were to start by rearranging this to solve for H3O, we get that the hydronium concentration is equal to Ka times our concentration of HA over base. And let's have some fun and be crazy and take the negative log of both sides. So the negative log of hydronium is equal to the negative log of Ka minus the log of HA over A minus. And so then the negative log of H3O is pH, and the negative log of Ka is pKa. So pH is equal to pKa plus the log. So if we do plus the log, then we're reversing this guy of A minus over HA. Could leave it as minus the log, but there's our derived equation, and there it is written a lot nicer. This is the Henderson-Hasselbalch equation. And this is used to calculate the pH of a buffer. If you know your acid and base concentrations, you know the pH, and you can calculate the pH because you can look up the pKa. So if we have two buffer solutions, both of them are 1 liter, and they have equal molar amounts of acetic acid and sodium acetate, it may seem like, oh, no matter what, they're both going to be the same power of a buffer, because even if they have But look at these difference in concentrations, 1 molar versus 0.1 and 0.1. The 1 molar solutions have more moles available, even though it's still 1 liter. Now you have 1 mole per liter versus 0.1 moles per liter. So because you have more moles available, that's going to have a higher buffering capacity than the 0.1 molar solutions because you have more moles of acid and base available to react. This is showing you the buffer solution and how the pH is going to change as we keep adding sodium hydroxide to this one. We started with the acetic acid and sodium acetate being equal in concentration, and we started a pH of, what is that, about 4.9-ish. And as we keep adding more and more sodium hydroxide, this pH is slowly going up until we hit this point that it's pointing out here. This is an increase of a pH of 1. So this is now an order of magnitude of 10 times more now OH minus that we've added. Okay, and so now as we keep adding more base, this buffering capacity, now that change in pH is getting more and more steep until eventually we hit this point where it just skyrockets because now we've gone above its buffering capacity.